Okay, now it is recording. Let me go ahead and share the screen. Let me know if you guys can see that. But yeah, hopefully you guys, okay, awesome. Yeah, you can see it. Cool. Yeah, so tonight is the quiz review session for the fluids chapter. I believe this is our last quiz, yeah. So, I'm still unsure if I'll hold like Tuesday review sessions from now until the end of the semester. But I mean, I see no reason to stop because whether you have a quiz or not, I mean, the last couple of weeks is just, it'd be nice to have like a review session for you guys. So I'll try my best to see if I can fit that into my schedule for the rest of the semester. The past semester I didn't do it, but I'll see if I can do it this semester. And like I said, I will try to make time to record the last quiz review session that was messed up with the audio. But yeah, so this is the last formal quiz that you guys will have. So for this review, as the other reviews, we will do some lecture slide review, and then we will also do a sample quiz that we can go over towards the end. But yeah, so starting off, just very simple, right? Fluid is a substance that can change shape to fit the container. Liquids and gases are both fluids, right? But there's a difference between them. So you have gases are compressible fluids, right? And liquids are pretty much incompressible. So you can compress a gas, you can put a gas, right, in a container, for example, if you've seen that in chemistry, right, with those different ideal gas laws, right? So you might have a container where you could kind of decrease the volume, that'll increase the pressure. If you increase the volume, that'll decrease the pressure. So gases are generally compressible, liquids are not, right? So even a moderate force on a gas will cause the volume to change, but even a large force on a liquid will not cause the volume to change. But then we also have concept of density when we're looking at pressure, right? We have density, that's mass over volume, that's pretty known. And then this is a very important conversion factor that you should know. 1 liter is equal to 1,000 centimeters cubed, or 1 liter is equal to 0.001 meters cubed. But yeah, this will be important, especially if you have what's it called? What do I want to say? Yeah, I think if you have grams per centimeter cubed or something for your density, and you want to get it to meters cubed, or if you want to switch things around and have things in liters or whatever, it's a useful conversion. I can't remember what I wanted to say for this slide exactly, in terms of the conversion, but this is an important conversion to know for sure. And specific gravity is a concept that just says it's just a ratio between the density of a substance and the density of water. So it's just the density of the substance divided by density of water, and that gives you specific gravity. So it just tells us how much greater the density of water is, or how less it is compared, I guess, to how much greater the density of the substance is compared to water, how less it is compared to water. So if you have 4 as your specific gravity, then you know the substance is 4 times as dense as water, for example. This is an example here for the conversion rate that we talked about here. The liter is equal to 1,000 centimeters cubed. If you wanted to convert or get the density of water, right, in grams per milliliter, well, that's 1 gram per milliliter for density of water. If we want to get it in, if we want to get density of mercury, for example, right, then you know for specific gravity, you have your density of your substance divided by density of water. Density of mercury here is 13,600 kilograms per meter cubed, divided by 1,000 kilograms per meter cubed for density of water. And so you know that that ratio is 13.6. So 13.6 tells us that the density of mercury is 13.6 times the density of water, right? So the density of water is a gram per milliliter, then 13.6 grams per milliliter is your density of mercury. Now, for water, we have it as 1,000 kilograms per meter cubed. So if we want to go from 1,000 kilograms per meter cubed to grams per liter, right, then we can convert from kilograms to grams, right, just by multiplying by 1,000, and then we can go from meters cubed to centimeters cubed, and then to milliliters. So if we have this meters cubed, we know that 1 meter is 1,000 centimeters, or not 1,000, 100 centimeters, my bad. 1 meter is 100 centimeters. And then to kind of get rid of the meters cubed, we have to take this whole thing to the third. And so you end up dividing by this, and you get, you'll have your meters cubed cancel out. You'll have centimeters cubed on the bottom. And then 1 centimeter cubed is equal to 1 milliliter. Now, alternatively, you can kind of jump through things a little bit, and say maybe like, well, I guess this is just more of a run around, but for 1 liter is equal to 1,000 centimeters cubed. Well, once you have your centimeters cubed, you can go to your liters and then go to your milliliters afterwards. Or if they were just asking for grams per liter, then you would use that conversion rate, which is 1 liter is equal to 1,000 centimeters cubed. You can just 1,000 centimeters cubed divided by 1 liter, and then your centimeters cubed would cancel out, and you'd be left with grams per liter as your units, for example, if they wanted that. Now we're talking about the most important thing in this chapter, which is pressure, right? So pressure is a ratio of force, magnitude of force that is, to the area at which the force is applied, right? Force divided by area gives you pressure. So that's newtons per meter squared, right? And that's Pascal's as well. So 1 Pascal is 1 Newton per meter squared. Pressure is the ratio of force to area, right? And so that pressure, for example, the liquid will exert a specific force, specific pressure on the walls of their containers, and then that force is exerted on everything that is in contact with the fluid, basically, right? So the fluid pressure pushes on all parts of the fluid itself. So if you had a container with holes in it, for example, it forces the fluid out of a container with holes. And pressure is not constant, right, throughout the entire fluid like that. So if you have differences in height, there's going to be a difference in pressure. And so specifically, the deeper you go, the bigger the pressure. So with more depth, you have higher pressure, right? So we'll kind of get into this later, but there's an explanation as to why that is specifically. I might as well just go ahead and explain it just so you guys understand like where that idea comes from for the rest of this chapter. But the idea is that I can actually just jump to the slide where it's at. Here we go. So the idea is that your atmosphere here, where you're at the atmosphere will determine your pressure, right? So we already said that increase in depth will increase your pressure. Now the reason that is because of the force of gravity and how it relates to the pressure equation. So we know pressure is equal to force divided by area, right? So what if your force, well, really the force is that determines pressure, right, in terms of depth and stuff. Well, force is force of gravity, right? So it's the force of gravity, mg, divided by the area at which mg is applied, right? So let's say this is our area that we're looking at, this cross-sectional area here. If it was kind of like a cylinder, for example. Now, as you increase in altitude, right, you go up into outer space, what happens to your force of gravity? This is just a very kind of like general kind of question. But yeah, anyone know what happens as you go up and up and up in a way? Yeah, force of gravity decreases, right? So the farther you get, right, you go into outer space, there's practically no gravity in outer space, right? So a decrease in gravity, while the area remains the same, would cause a decrease in what? So decrease in gravity, force of gravity, decrease in pressure, exactly. So that's the idea here. That's why pressure increases with depth. As you get closer, right, to Earth or to the center of the Earth, right, you're going to find that gravity is going to increase. And so that's why it increases with depth. Here's space where force of gravity is pretty much zero. As you increase in your depth, right, as you get closer to the Earth's surface, right, as you even get closer to the center of the Earth, right, so if you go below sea level, then you start to see increases in gravity and therefore an increase in pressure. So with depth, there's an increase in pressure because of an increase in gravity. right? And then as you increase in height, so let's say from Earth here, we take a rocket ship to space, as we increase our height, we find that there's a decrease in pressure because force of gravity is going to get lower, right? So that's also because the air is also more dense here at the bottom near the Earth, and it's less dense in outer space, right? And that kind of makes sense because if you have force of gravity as mg, right? Well, density is mass divided by volume. If your volume's constant, right? Or my bad. If you have density is equal to mass divided by volume, right? Then if the density is increasing, then you can see because it's related to mass divided by volume, then we can think that I want to say mass, well, maybe that's a bad example. Maybe not the mass increases per se, but yeah, I don't know if they're exactly related. But anyway, you get the point that as you increase in altitude, as you increase in height, there's a decrease in pressure. As you increase in depth, right, get closer to the Earth, then you have a increase in pressure. But yeah. So if you're saying greater width, more pressure. So in terms of like, if you mean like width, like area, like the diameter, for example, right? Is that what you're talking about? Yeah. So if you increase pressure, or if you increase the area, my bad. If you increase the area, then you should see a decrease in pressure. If you increase the area, you should see a decrease in pressure. But yeah. Now, that's at least from this kind of perspective here. From this perspective, at least from the equation standpoint, if I decrease the area at which I apply a certain force, then I should see a, or my bad, not decrease the, if I increase the area at which I'm applying a certain force, then I should see a decrease in pressure. If I decrease the area at which I'm applying a certain force, I should see an increase in pressure, right? But whether width or increase in area relates to more or less pressure will vary a little bit once we get to like Bernoulli's equation and stuff, and I'll explain why here in a sec. But let me move back up here to the pressure stuff. So that's pressure, right? We have an example here. Consider a column filled with water. Top of the column has an area of 10 centimeters squared. What is the force exerted by the atmosphere on the top of this column of water? So we know that P is equal to F over A, right? So if we have the pressure as atmospheric pressure over here, 10 to the fifth, right? Then we just multiply by the area to get the force that is exerted by the atmosphere on the top of the column of water. So 10 centimeters squared, we'll convert it to meters squared. 10 centimeters squared, convert it to meters squared. That's 0.001 meters squared. Multiply by the 10 to the fifth pascals, and that gives you a force of 100 newtons, for example. That's the atmosphere on water. Now, what force does the water exert back on the air? Well, it would have to be an equal and opposite force, right, in order for there to be no net motion. Because if we have just this column of water here, just stationary, like just a glass of water, for example, then whatever the pressure from the, or whatever force the atmosphere is exerting on the water, so atmosphere on water, there has to be an equal but opposite water on atmosphere in order for there to be no motion to the fluid whatsoever. Viscosity and flow, or not viscosity, yeah, viscosity, my bad. Viscosity is like, it's not as tested, I don't think, in this specific chapter. I'm not sure exactly, or I know why they include it, but I guess it's not completely pertinent to this week's stuff, but viscosity is essentially just a measure of like thickness or stickiness of a fluid. We kind of already did this back when we did Reynolds number for the last chapter. 1 Pascal second is 1 Newton times second per meter squared. And so the thicker a liquid is that you can think of, right? So air versus like honey, well, the honey is going to be a lot thicker, have a lot more viscosity than air, for example. So viscosity is a measure of thickness or stickiness to a fluid. This is very simple again. So velocity and flow. Fluids can move, they have a velocity at every point. That velocity is not necessarily constant. And the velocity can differ depending on what region we're looking at, right? Some regions might move fast, might move slow. and that'll depend as well on like area, which we mentioned earlier. So that's something we're going to get to with Bernoulli's equation. But other properties that we'll be looking at here, I think maybe either this week or next week, I can't remember. I don't know if you guys are doing the second week of fluids this week, but you'll discuss surface tension as well and something called the bulk modulus, but don't really have to focus on that now. When you have a pressure being exerted, right, that pressure is everywhere in the fluid. Different parts of the fluid are pushing against each other, right? Now, this part is really important. So in a liquid, pressure increases rapidly with depth below the surface, like I said earlier, right? So if you increase your depth, you're going to increase your pressure. In a gas, however, the pressure is nearly the same at all points, at least for laboratory size containers, which is going to be most of the situations that you'll see if you have the gas that we're looking at. Mostly that we're going to be looking at, like water or oil or, liquids, for the most part. Would you want to say anything else for this slide? No, I don't think so. Well, yeah, I mean, pressure, once again, is equal to force divided by area, right? So the force compresses the spring right here. So if you have like water, right, pressing down on this piston, the force of the water, right, will compress the spring, and we can figure out that force because there's a specific spring constant and stuff. But so in that case, like if you were to ask you something like that, yeah, go ahead. Someone have a question? Mm-hmm. Yeah, that's an excellent question. Yeah, so absolutely, that's something I should have mentioned earlier as well. Thank you for alerting me to that. But anytime you have any liquid in contact with just the air up here, that pressure at this point here, the air, liquid, air, gas interface, that pressure is going to be 1 atmosphere. 1 atmosphere is equal to 10 to the 5th pascals. It's also equal to 760 torr. It's also equal to 760 millimeters of mercury, right? So whenever you have this liquid, or just a fluid, right, in general, in contact with air, directly in contact with air, right, between the air, fluid, right, liquid or fluid interface, right, at that point, the pressure is going to be 1 atmosphere, or 10 to the 5th pascals, or 760 torr, or 760 millimeters of mercury, right? So someone also had a question about like how to convert between all these, right? So if I have, let's say if I had 10 to the 6th pascals and I want to convert it to atmospheres, for example. Well, I know that 1 atmosphere is 10 to the 5th pascals. So I divide, pascals goes with pascals, I get the number of atmospheres, right? Well, what if I wanted to go from pascals to something else like torr or millimeters of mercury? Well, then I know still that 1 atmosphere is equal to 10 to the 5th pascals. Pascals will cancel out with pascals. I'll have atmospheres on top. I know that 1 atmosphere is the same as 760 torr, right? Atmosphere will cancel out with atmosphere. Pascals cancel out with pascals. Now you're left with torr on top. Same thing for millimeters of mercury as well. It's 760 millimeters of mercury. So 760 millimeters of mercury is equal to 1 atmosphere. So any of those conversions, right? And you can do, if I have like 810 millimeters of mercury, well, I can just multiply by, or divide by 760 millimeters of mercury. That's 1 atmosphere, right? And if I want to go from atmospheres then to pascals, then times 10 to the 5th pascals in 1 atmosphere, right? So that way, millimeters of mercury cancel out, atmospheres canceled out with atmosphere, and you're left with pascals on top. But that's how to kind of convert. So 1 atmosphere is 10 to the 5th pascals. It's also equal to 760 torr. It's also equal to 760 millimeters of mercury. So thank you for reminding me of that. But yeah, I think that's about it for this slide here. Now, this slide is going to go over kind of like the derivation of the hydrostatic pressure equation, which is the PA plus rho GHA is equal to PB plus rho GHB. Sometimes, like, forgive me, I might just say like P for this because they just all look like P's, but I call this fancy P. It's rho, Greek letter rho, but it looks fancy, so fancy P. But this is the kind of derivation that we're going to see for the hydrostatic pressure equation. So you have force of gravity, right, pointing downwards pretty much anywhere in the liquid. Let's say if you wanted to figure out what's the force exerted by the liquid here at this point, or by the atmosphere on the liquid here at this point, right? What about this point? Well, the idea is that you have all these forces. These forces are going to be giving us pressures, because remember, pressure is equal to force divided by area. So the area is the same, cross-sectional area is the same everywhere, right? Well, it's just everything's going to differ then based on the force, right? So if we look at P is equal to F over A, well, the force at point A should be equal to the pressure at A times the area, right? Because pressure is equal to force A times area, divided by area, I mean. So PA is equal to FA. So the force at A is equal to the pressure at A times the area, right? Now, at point B, if we wanted to figure out the force there, right, we have force at B divided by area at B is equal to the pressure at B. So the pressure at B multiplied by the area should give us the force at B. Now, why are we looking at forces and stuff and not necessarily just the pressures like we have here? Well, like we said, so pressure is equal to force divided by area. Now, in order for the liquid to be completely motionless at this point, essentially, as we mentioned before, like if you just have a glass of water, that glass of water, the water isn't moving inside, right? So how does that happen? Well, all the forces would have to cancel out. There would have to be a net force of 0. So if your net force is 0, it's made up of the component forces, right? So if I wanted to figure out, what is it? I'm just looking at like vertical forces, right? At different points. So if this was my B and this was my A, like if I want to figure out the pressure at B, pressure at A, or the force of A, force of B, well, F net is equal to 0. I know that force at A will have to cancel out with force of B, and it will cancel out with force of gravity, right? Because there's force exerted by the atmosphere at this point, force exerted by the atmosphere at this point, right? And then you also have force of gravity always pointing downwards, right? So for force of A, it'll be pointing downwards like this, right? Because we have the force on the top there. And we also have force of gravity that cancels out, or not cancels out, I mean just also pointing downwards. So it'd be saying like, we could say like F would be like minus FA minus FG, and you also have FB plus FB here, right? And so in that case, you can see that if you have FB is the one that's pointing upwards, minus MG minus FA. So minus those two downward facing forces. So you can see then that your force at B should equal the sum of the force of gravity and the force at point A. And so when we say that, right, force at B is equal to mg plus Fa, we can convert these forces to pressure values. So FB, we already said that was PBA. So the pressure at B times the area, right? And then for force of gravity, well, if pressure is equal to force over area, then force is force of gravity, which is mg divided by area. So it would be like the pressure times the area is equal to mg, right? But we know that this force here, if you remember from the like the buoyancy chapter, we also have it written as density times the volume times gravity, right? Because density is mass divided by volume. Your volumes would cancel out and you're left with mg there. So they can also write it as density times volume times gravity. And then you have force A, that's equal to the pressure at A times the area. So if we convert this volume here as well to area times height, because area, if we have like area of a cylinder, for example, would be the cross-sectional area of the circle times the height of the cylinder, that would give us the volume. So area times height is the volume. And then we can see, right, we have this kind of equation here. PBA is equal to PA times A plus density times area times height times G. And so if we were to kind of like pull out the area there, so we have PBA is equal to area times PA plus rho HG, right? Density HG. Well, the areas will cancel out, and then you're just left with PB is equal to PA plus rho HG, or rho GH, right? So you can see here that's very similar to what we're seeing with the hydrostatic equation, right? And this actually makes perfect sense, because if you're at the bottom here and the bottom is our reference point, well, based on the hydrostatic pressure equation that we'll look at here in a sec, if your height is your reference point here at the bottom, or if your reference point here is at the bottom, then we can say that the bottom height is 0. That way, anything moving upwards is going to be a positive height. So then you can say that, well, height at the bottom is 0, and then height at the top will be a positive answer, right? And so this whole term cancels out, and you're left with PB is equal to PA plus PGHA, right? And so you can see that's what happens here. PB is equal to PA plus PGHA. So that's the derivation there of the hydrostatic pressure equation. But yeah, I don't know if there's anything else I wanted to kind of talk about there. But I think that might be it. Oops. For at least this slide here. But you don't even have to worry about like the derivation of this stuff. The most important thing is to understand that this is the hydrostatic pressure equation, right? You have your pressure at the specific point A plus the density times the gravity times the height at that point A. Like I said, usually we start from the bottom and we go upwards, right? Start from the bottom and you go upwards. That way, if you have your bottom height is 0, right? Then you can see that PB is equal to PA plus rho GHA. Well, that tells you automatically then that what? How does PA compare to PB in that case from that equation? Just by looking at that equation, what does that tell you? If PB is at the bottom and we set the bottom to be height of 0, and this thing cancels out, if PB is equal to PA plus another term, what does that tell you about PB versus PA? Exactly, right? So we already know from just the conceptual aspect, right, looking at the force of gravity, that as we go increase in depth, move downwards, right, we're going to see an increase in pressure. If we move upwards, we should see a decrease in pressure. Now, from the equation standpoint, if we make our height 0, like we said, this term cancels out, and so we see that PB is equal to the sum of the pressure at A plus a whole nother term, right? So if this is like 10 atmospheres plus another 12 here, then we can see that it's 22 for the pressure at B, right? So from the equation, at least, you're absolutely right. We can see that there's going to be a higher pressure at the bottom point and a lower pressure at the top point, right? But yeah, and like I said, it's just preferable to start from the bottom and go upwards, and that's how you write your equations. Otherwise, I've seen some people send me some problems that they'll start from the top and go downwards, but the mistake that they're making is that if, for example, if we start from the top and we say that A is a height of 0, well, then this term goes to 0. So then you could say PA is equal to PB plus rho GHB, right? Well, then you can't say, if this is 10 centimeters, right? The height is 10 centimeters, then you can't just have your height be 10 centimeters, positive 10. It has to be negative 10, because you're moving downwards, because you're technically decreasing in height. You're increasing in depth, but decreasing in height. So if you're starting from the top and going downwards, make sure your height is going to be negative then for that downward point. And if you're going from the bottom moving upwards, then make sure that your height is positive, right? So I think it's just preferable to start from the bottom. But yeah, Aries, did you have another question? Yeah, exactly. So like, I mean, you can also think about it this way. So we know for a fact, like I've already explained, like the conceptual aspect, that regardless of what happens, just scientifically, and we can prove it multiple different ways, right? As you decrease in height or as you increase in depth, like if you go lower, if you go scuba diving, you're going to see an increase in pressure as you move downwards. As you move towards the center of the earth, force of gravity increases, right? And so you're going to see an increase in pressure as you move downwards. As you move upwards, away from the center of the earth towards outer space, force of gravity will decrease, right? So you should see a decrease in pressure as you move upwards, right? That's why your ears pop in the airplane. So with a decrease in pressure, right, then we know, like I said, if we start from the bottom, if we start from HB here at the bottom here, bottom B, think B as bottom, right? Usually think B as bottom. That's what I like to think of it as. B is bottom. So if HB, we start here at the bottom, is 0. That's our reference point. That's our reference height. Then this term becomes 0. Then we can see that the pressure at B is equal to the sum of pressure of A plus a whole nother term. So like I said, if this pressure at A was 10 plus 12, then we can see that the pressure is 22, right? And so that makes sense once again, because if we go downwards, increase in pressure. If we go upwards, increase. If we go downwards, increase in pressure. If we go upwards, decrease in pressure. My bad. And so if we reverse that, if we start from the top and we go downwards like this, well, then our height, A, would be our reference point. This is our reference point, so we're measuring from this point. So HA should be 0. So this term goes to 0. Well, then that shows us that PA is equal to PB plus rho GHB. Well, that shows us, similar to how we saw with PB is equal to PA plus rho GHA, that shows us that PA is the sum of PB plus a whole other term. Well, if we were to say, once again, this is 10 plus 12, right, then we should see 22 again. But that doesn't make any sense. How would the pressure at PA be greater than the pressure at PB? 22 versus 10. That doesn't make any sense. We can't have that, right? In order to adjust for that seemingly, correct setup for the equation there, in order to adjust for this, we have to see that the pressure the height, that we move as we move downwards, the height will be negative. Right? So if we move downwards, negative, upwards, positive. Just think positive and negative y-axes, right? So as you move downwards from A to B, if you make your A your reference point, if you make A 0, then anything below 0 is going to be negative 10 centimeters, for example. Anything from 0 above is going to be a positive 10 centimeters. So when you're writing PA is equal to PB plus rho GHB, well, then just make your rho GHB, or make your HB, negative 10 centimeters. That way you can see then, if this is 10 and this is still 12, it would be 10 minus 12, right? And so then you'd say, at least theoretically, PA would be negative 2. And so you could see that negative 2 is less than 10. Does that make sense? Okay, that makes sense as well, Eric, just to clear up that whole depth versus height thing. Okay, awesome. Yeah, I prefer to look at it as a height as opposed to depth. It's just a lot easier to think about it as height. Okay. Now, as we said earlier, as Eric mentioned earlier as well, anything that you have, any fluid that's in contact with the surface or air is going to have a pressure of 1 atmosphere, or 10 to the 5th pascals, or 760 torr, 760 millimeters of mercury, right? Now, why do you think this isn't possible here, for you to have the pressure be 1 atmosphere here and 1 atmosphere there? Or at least with these heights. Why is this impossible and this is possible? Yeah, so exactly. So if we know for a fact that any surface of a fluid in contact with the air should have atmospheric pressure, right? Well, if PA, then, if we call this PA and this PB, right? Well, if PA is equal to PB, then if this is 10 to the 5th pascals, this is 10 to the 5th pascals, they should cancel each other out. And so then you're just left with rho GHA and rho GHB. having to be equal to each other. Well, the density, water is water. Math is math. Water is water, right? Gravity is gravity. Now, height of A has to equal height of B. These are different heights. So this is not possible. However, we can see here that if these are the same height, same fluid, same gravity, same density, right? Same pressure point here and here in contact with the atmosphere. If this is 10 to the 5th pascals atmospheric pressure, this is 10 to the 5th, they should be the same heights as well. And so you can see here, this is a general rule that any two pressures, or any two, at any, like, well, yeah, I guess any two pressures, if they're at the same height, so this is height 1, this is height 2, oops, height 2, ooh, what happened here? There, height 2, right? Then we should see the same pressure there based on the hydrostatic pressure equation. The only time that we might not see the same pressure at the same height is if we also have movement of a fluid, which is something we're going to get to here with Bernoulli's equation. But otherwise, two pressure points at the same height will have the same pressure, unless there's movement of the fluid, in which case there might be a difference in pressure. But same thing here at pressure 1, pressure 2, they're at the same height, height 1, height 2, so they should have the same pressure, right? This, they're asking us about the pressure at the closed section, right? Pressure here, as opposed to, well, I guess, yeah, I mean, really, if you wanted to get the pressure here, for example, let's say pressure closed, right? And you wanted to figure out the pressure closed there. Well, what other pressure terms do you think you know? Someone name them out. Oh, I just meant like what pressure points? Like, yeah. No worries. So I see PA. So you mean like atmospheric pressure? Yeah. So we know atmospheric pressure. Now, where would be the point that we see atmospheric pressure? Here or here or here or where? Yeah, the not close side, and more specifically, right, at the very top of the column here, where it's in contact with air, right? So we know that at this point there's atmospheric pressure, and that's equal to 10 to the 5th pascals, right? So if this is 10 to the 5th pascals, then we can compare it to this P closed here, using the hydrostatic pressure equation to figure out. So PA at the top here, plus rho GHA, is equal to PB plus rho GHB, right? Now, we can kind of just look at the bottom point here. We can say that the bottom point, PB, right? PB is the pressure that we're looking for. That's the P closed. That's our reference height, so that starts at 0. So this whole term goes to 0, and then we're left with PA plus rho GHA, right? So PA here at the top is at 10 to the 5th pascals, and then we just add the density times the gravity times the height, and that's height going upwards. So if this is 0, right, if this was 40, from here to here was 40, right? From here to here is 40. But if we're making this our 0 point, then from here to here, what should it be? 60, exactly, right? So from here to here is 60, from here to here is 40, right? If we're making this our arbitrary like 0 point, right, to make it easier to solve the equation, then from here upwards should be 60, right? And so once we do that, we can figure out our PB. Now, it's also important to realize once again that this pressure here at the closed section should be exactly equal to the pressure there. So if they were asking, okay, what's the pressure P3 here? Well, the P3 is going to be equal to the P closed because they're at the same height, right? So if they're at the same height, they should have the same pressure unless there's movement of the fluid. So once again, yeah, there's another kind of example of it. So if you have P1 here, P2 there, right? These should have the same pressure because they're at the same height. Now, what if, for example, you had this difference in type of fluid here from gas versus liquid, right? So what you can do is figure out basically what is the pressure at P2 compared to the atmospheric pressure here at the top, right? What's the pressure at this depth here, right? So if we have, this is our arbitrary 0 point, so H2 would be 0, right? So if we were to say like this is PA, so PA plus rho GHA would just equal to be P2 or PB, right? Because then H2 would be 0, so that rho GH2, that would go to 0 because the height is 0. And so then once we figure out our P2 is going to be exactly equal to P1 because the pressure is the same at the same height. Yeah, so if we were going back here, the dashed line, we can make that our 0 centimeter point because that's what we're measuring from. Alternatively, which you could do, but this is just going to be a lot more math to do, is you could leave it as this, right? But instead of writing 0 as your height, you can say, oh, height B is at 40 and height A is at 100. But it's just much easier to then say that, okay, this is our 0 point, this thing cancels out, and then we're just measuring from here upwards, and that's 60. Does that make sense? Okay. And then there's the concept of gauge pressure. A lot of people had issues with this as well. Gauge pressure is literally just the absolute pressure that you have minus 1 atmosphere. It basically just tells us how much higher or lower the pressure of a specific fluid is, right, or specific substance is compared to atmospheric pressure. So if I say that if my absolute pressure of a gas, right, is 10 to the 6th, then I subtract 10 to the 5th pascals, which is my atmospheric. So this is my absolute pressure of my substance minus my atmospheric pressure, and it'll tell me exactly how much above or below my pressure is from the atmospheric pressure. So if I have like an absolute pressure that is higher than my atmospheric pressure, should I see a positive or negative gauge reading, for example? If absolute is higher than atmospheric, should I see a positive or negative gauge reading? Yeah, so if I have a absolute pressure that is higher than my atmospheric, would I have a positive or negative gauge reading? Yeah, exactly. So if you have absolute is greater, then if P gauge is equal to absolute minus atmospheric, if this is bigger than this one, right? If this is 12 and this is 10, then you have 2, positive 2. Now, if my absolute is lower, right? If it's smaller, then if absolute is 10 and atmospheric is 12, then I should see a negative gauge reading, for example, right? But that's the concept of gauge pressure as well. It's the absolute gas pressure that you have, or absolute liquid pressure, right, minus the atmospheric pressure. That could be in torr, that can be millimeters of mercury, that can be in atmospheres, pascals, whatever. Just make sure that you're subtracting the two values with the same units. So you can't just say like 10 to the 5th pascals minus 1 atmosphere, right? You can't do that. You have to say 10 to the 5th pascals minus another 10 to the 5th pascals, right? So what is then the gauge pressure of atmospheric pressure? So I told you I want the gauge pressure at this point, right? What would the gauge pressure be here? 0, right? Excellent. So if P gauge is equal to absolute pressure minus atmospheric pressure, well, if we know that the pressure at this point is 10 to the 5th and the atmospheric is 10 to the 5th, then they should cancel out. So any time where you have a point that is equal to atmospheric pressure, it has a gauge pressure of 0. All right. This problem, I think they were just asking you to figure out the gauge pressure of the gas, right? So we already kind of looked at this earlier right here where I said, okay, you can compare the atmospheric pressure here to the pressure at point 2. So you have HB, which is our point 2 here, as a reference height, and that's going to be 0, right? So this whole thing goes to 0. So then you're left with P2, or PB, is equal to PA plus rho GHA. So 10 to the 5th pascals, which is at the top here, plus the density of the mercury times 10 times 30 centimeters or 0.3 meters, right? That'll give us the pressure at point 2, right? Now, pressure at point 2, like we said, is going to be equal to the pressure of the gas, because P1 is equal to P2 at the same heights. So then we have this answer in pascals. We can convert it to millimeters of mercury, for example, right? I think that's that might have been the units that they wanted. But you convert it to millimeters of mercury and then subtract, for example, like if you have 1,070 millimeters of mercury, you subtract by the atmospheric pressure in millimeters of mercury, which is 760, and that gives you your gauge pressure. So 1,070 minus 760, 310 roughly millimeters of mercury is our gauge pressure. So that tells us that the gas pressure is 310 millimeters of mercury above the atmospheric pressure, basically. And then we also have, like, for example, you might have a situation where, like, what I have here, H is negative, so let me just read this real quick. So, okay. I guess I was saying, like, if you were to have like a height here and a height there, and the density of the height of the mercury, for example, was lower than this point, then the gas pressure would be less than atmospheric. And that kind of makes sense because think of the atmospheric pressure, right? Once again, pressure is equal to force divided by area. So if the atmospheric pressure is greater than the gas pressure, then you'll see this kind of pushing kind of more on the gas. And so you'll see a decrease in height for the liquid, for the liquid basically, right? Because the liquid will show you the atmospheric pressure. And so if the atmospheric pressure is a lot stronger than or a lot greater than the gas pressure, then it's going to be pushing down a lot and going to be pushing upwards here on the gas to a point where you can see here, like, it'll push downwards a lot more and push the gas upwards like that. But if you have an example here where the gas pressure is actually greater, right? Well, the gas pressure is going to exert more pressure here, kind of pushing the mercury upwards against the atmospheric pressure. That's kind of what we see. Without an example, I don't want to kind of like go too much in depth with this example here, but you have the basics and the foundations to be able to understand like an example like that. But now this here for a barometer, right? Really, I don't think you ever have to like really just have an example. I don't think there's ever an example you have to like read a manometer or read a barometer, but you do have to be familiar with how they kind of like work in a sense, or at least just in general how the how like fluid pressure mechanics work. So if they were to tell you that, or if they wanted you to figure out the atmospheric pressure, so here, what is the gauge pressure of the atmosphere? What is the gauge pressure of the atmosphere? Well, in reality, atmospheric pressure is not exactly 10 to the 5th pascals, right? It might be 10 to the 5th on a good day, but otherwise it kind of fluctuates a little bit. I believe it fluctuates between like 80 something kilopascals to 100 something kilopascal. 102 something kilopascals, right? So it kind of varies a little bit, which makes sense. I mean, it's nature. It's not going to be exactly constant all the time. So if we wanted to figure out the actual atmospheric pressure, maybe for example on a bad day where it's a little bit less, then we can use that using we can figure that out using a barometer, right? So if we have this barometer here, we can see that in this vacuum we'll have zero pressure here at the top of this this tube, right? And so if we then wanted to figure out kind of like the pressure at 2, because the pressure at 2 will be the exact same as the pressure at 1. So let's look at things inside the tube and then compare them to outside the tube. So the pressure at 2, we can figure that out using the hydrostatic pressure equation. If we know that at the top, the pressure is 0 because it's a vacuum, then PA goes to 0. HB is our reference height, so we start from the bottom, now we go to the top. So HB is 0, and so this whole term goes to 0, and then you're left with PB is just equal to rho GHA. So then you get PB. Well, we know that PB here at the bottom, where P2, right, P2 is the same as PB. P2 here is going to be equal to P1 because they're at the same height. Well, we saw that this was equal to 95,200 pascals, right? So about 95.2 kilopascals. It's a little bit less than your normal kind of constant value. So you can see that it's 0.95 atmosphere versus 1 atmosphere. So it's a little bit less than atmospheric pressure, or the atmospheric pressure value that we're used to. So if we want to figure out the gauge pressure, then we just take that 0.952 atmospheres minus 1 atmosphere, and then we can see that the gauge reading would indeed be negative 0.05 atmospheres, for example. But yeah. This one? Yeah, so yep, so if the fluid is different, yeah, you'd have to kind of find 2 points where at the same height, right? And then compare it to a known value. So for example, like we know P1 and P2 are at the same heights, but since there's differences in fluid here, right, there's going to be a difference in density, so that makes it a little bit more difficult to figure out the exact like pressure at this point. But we know that P2 and P1 are at the same height, so they should have the same pressure. And we also know here that it's atmospheric. So if we can figure out what the pressure is from the top to the bottom, then once we get P2, we can set that equal to P1, and then we have the pressure of the gas at that point. Yeah, practically you can use just any 2 points. But I mean, in that case, right, like you still have that same concept where any 2 points at the same height will have the same pressure. But yeah, essentially you'd be able to use any 2 points to figure out the kind of like the pressure change between them. But still, P1, P2, right, if they're at the same height, then they have the same pressure. So like the example that you might be talking about is kind of like here where we have all water. But the idea here is that, once again, if I want to figure out what the pressure here is at the closed point, right, then I can think that, okay, well, closed point here is going to equal the same height over there. So the pressure here is going to equal the pressure there because it's at the same height. Then I can compare the pressure here to the pressure of the atmosphere up top here. So this is A, B, C. So B is equal to C, and then B is greater than A. And we can compare these two via hydrostatic pressure equation. And then B would be equal to C just based on the similar height, or the same height. Does that make sense? So for the hydrostatic pressure equation, whenever we are finding PA or PB, one of them will be equal to 10 to the fifth. I mean, yeah, if you're comparing them to a point that's in contact with the atmosphere, one of them will have to be equal to 10 to the fifth. But otherwise, like, if you have just 2 points, right, PA and PB are just 2 different pressure points. So usually we'll have one of them be compared to atmospheric. That's usually almost always a given. But they might give you a different point. They might just say like, oh, pressure at point A, here's pressure at point B, here's pressure at point C. Well, then this pressure would be something other than atmospheric. You can still compare it to B via the hydrostatic pressure equation, and then B is equal to C, for example, because they're at the same height. So they might not always compare it to the something in contact with the atmosphere directly, something where there would be 10 to the fifth pascals, but most of the time they do. Most of the time it's an option, right? But other times, like, you can just compare 2 different pressure point values using the hydrostatic pressure equation. Yep, no worries. Have a good night. So yeah, I mean, for the hydrostatic pressure equation, any two pressure points you can use to compare to each other. It just, if you don't have any other points in between that you could compare to, then usually it's going to be one is at the top at atmospheric, and then one is at the bottom towards that point that you're trying to figure out. But, yeah. Now, this is kind of a quick check that is just asking you about like the correct equilibrium position. So we know that oil is less dense than water. So if we go by the hydrostatic pressure equation, right? If, for example, this point here and this point there should have the same pressure atmospheric, right? Here and here should be 10 to the 5th pascals. Then we know that PA and PB, or P oil and P water should be the same. So these should cancel out. Now the differences would then be differences in density or differences in height, right? So density of oil is less than the density of water. So density of oil is less than density of water, right? So if I decrease density of oil, then I have to increase the height in order for things to be equal on either end. Well, not increase, but like you get the idea where like if the water density is increasing, or if not increasing, but if the water density is greater, then the height of water has to be less in order for there to be an equal value on either side. So we can see here that the height of the oil is greater than the height of the water, right? Because, for example, like I said, for rho GHA is equal to rho GHB, right? Well, if density is less, right, and density is greater here, so density of oil is less than density of water, then the height of the oil has to be greater than the height of the water. You can see the arrows kind of cancel out. And if we did this mathematically, right, if we, for example, if we were to say that this term here, rho G and rho G, right, if this was 3 times 4, right, 12. If I want to get 12 on the same side here, but my density is greater, then this might be, this term here, rho G, might be 6. Maybe I have twice the density. So 6. How can I get 12? Well, I multiply by 2. So you can see here that the height, 2 versus 4, the height has to be lower for water. This is 2 versus 4, right? The height has to be lower for water as compared to the height of the oil because the density is greater for water. So if I decrease density, or if I have lower density, I must have a greater height. If I have greater density, I must have a lower height in order for both sides of the equation to be the same. Let's see here. These are just more kind of examples of this hydrostatic pressure stuff. I think you guys kind of got the gist. I would just want to make sure to cover the like this stuff here, the Pascal's Principle and the Bernoulli stuff and continuity. Just want to make sure we have enough time for that. But here again, we have buoyancy. I don't think buoyancy is like very heavily tested in this chapter at all. I don't even remember an equation about buoyancy, to be honest, and anything here. But it's just the upward force of a liquid. Remember, it's equal to the mass of the fluid times the gravity, and it's equal to the density of the fluid times the volume displaced of the fluid times gravity. Right? It's just another one of those forces there. So let me see here what I want to say for this slide. So yeah, I think I might have forgotten an extra term here, FB. So F buoyancy. Buoyancy is pointing upwards, right? FB is pointing upwards, and you have top, the force exerted at the top here pointing downwards, force exerted from the bottom here pointing upwards. So FB minus F top plus F bottom, basically. And so for your net force, you should see that your buoyancy wait, hold up. That doesn't make any sense. F top plus F bottom. Yeah, I don't know about that one. Yeah, that might be, I don't know if that's a typo or not, but this slide isn't like super important anyway, to be honest. Okay, we can move on to Pascal's principle. So for Pascal's principle, it just tells us that any change in pressure that we see applied to any surface of an enclosed incompressible fluid, so incompressible like water, not gas. Gas is compressible. So any incompressible fluid, right, it's going to be liquid. Any change in pressure that we see on that enclosed incompressible fluid will cause an equal change in pressure at every single point. So if we apply a specific force here to give a change in pressure, then that change in pressure has to be equal at every single point in the fluid, right? So if we increase PA here, then PB, for example, here has to increase as well to the same point, obviously, or at least an equal change in pressure, right? Now, the idea here is that, like, if you have a pressure applied at point 1 here, pressure is equal to force 1 over an area, right? Well, force 1 is applied at a smaller area, right? So if I have a smaller area, if I decrease my area, right, as compared to this big area right here, if I decrease my area, that increases my pressure, right? So if I'm physically pushing down here with a specific force over a specific area, then compared to the second area, P2 is equal to force 2 over A. Well, the area is a lot larger. If the area is a lot larger, then your pressure will decrease. Well, I don't want the pressure to decrease. It actually increased when I pressed down over here. So if I want to make sure to overcome that natural decrease in pressure because of that larger area, then there has to be a much larger force exerted as well to kind of counteract that, right? And so that's why you see a much larger force on the right-hand side. If I push down with a small force, with a small area, right, I'm going to have a larger force with a larger area. But yeah, it's just a matter of like looking at, okay, well, F1 over A1. A1 is smaller than A2, right? So if I wanted to say F1 over A1 has to equal F2 over A2, right? Well, if A1 is 2 and A2 is 4, right? If it's double the area, if I applied a force of 60 newtons here, right, then I have to apply a force of 120 newtons there in order to maintain the same pressure. Because once again, by Pascal's principle, any change in pressure here, there, any change in pressure applied to any surface of an enclosed incompressible fluid, if I apply a specific change in pressure, a pressure of 30 pascals, for example, right, that pressure has to also be exerted on this big area right here. How do I exert this same pressure? Well, if I have a much larger area, right, if this was 60, if it kept the same force, 60 divided by 4, well, that's 15, right? That's not going to give me the same pressure of 30 newtons on the left-hand side. So then the force applied on that right-hand side actually has to be a lot bigger, right, to counteract that natural decrease in pressure because of the larger area. So normally, if you have a larger area, you have a decrease in pressure. To counteract that and make sure that the pressure is the same on every single point of the fluid, then your force applied then on the right-hand side is a lot bigger to maintain the same pressure, right? So that's the idea there for Pascal's principle as well. Okay. Yeah, we can. Yeah, I want to go over this one. So if they told you if you push down on the left piston with a force magnitude 10 newtons, with what force does the water push up on the right piston, right? So same thing here, like F1A divided by A is equal to F2 divided by A, A2, A1, right? So F1 is equal to 10. I want to figure out the pressure at P1. So I have the radius of the left piston is 1 centimeter or 0.01 meters. Pi r squared is my area. So then I can figure out my pressure, which is 31,831 pascals, for example, right? That pressure, like I said, has to be the same on this right-hand side as well. So if F2 well, you know that pressure 2 is equal to force 2 times A, or divided by A. So I multiply the area, so P2 times area is equal to F2. Well, the pressure should just be equal to the pressure exerted here on the left-hand side. So that's why you see 31,831 multiplied by the area of the larger piston here, and that gives me a force of 90 newtons instead of 10. So you can see on the right-hand side, 9 times the force to maintain the same pressure. Now, with this example here, a cylinder with a movable piston filled with a uniform fluid, if the corks are all in equally tightly, which are most likely to pop when we hit the piston, right? So for this example, think about pressure, a difference in pressure, meaning a difference in force exerted. If I apply more force to this cork, for example, it's going to pop off probably a little bit easier than if I apply less force to this same cork here. Now, if we think about force as being pressure, or my bad, not the other way around. If we think about pressure, right, being a force exerted over a specific area, then the areas here are all the same. The areas here are all the same. So, which one would essentially exert the largest force, right? Which one would theoretically have the greatest pressure? Well, if we're pushing this way, you might think, okay, well, cork 3, because if we kind of like flip it over, I can't really flip over the slide, but you would think that as you kind of increase in your depth, then this one would pop off the most, for example. But we're thinking about things up and down like this. And so 3 isn't the one to pop off easiest. It's 4 that's popping off the easiest, because if you look at the heights, the difference in heights here, right? If you were to compare, like, if this was our PB, this is our PA, right? If B is our bottom point, HB is 0 because it's our reference height, and then you're left with PA plus rho GHA. Well, if A is here at the top, then you can see already that the bottom point is going to have a larger pressure. If you compare it to 3 as well, still number 4 will have a larger pressure because it's at the bottom here compared to these two. So more depth means more pressure means more force means it's going to pop off easier. So bigger pressure, more depth means bigger pressure, more pressure means bigger force, more force means it'll knock the cork out easier, and pressure is the biggest at the bottom. Fluid dynamics, I mean, this viscosity stuff, I don't think it's like very important at the moment. Correct me if I'm wrong. Like, have you guys seen any like viscosity problems so far with this fluid stuff? I think it's mostly been like hydrostatic pressure equation and Bernoulli stuff, but I'm pretty sure you might go into it this week. But like, it's just not. Yeah, go ahead, Matthew. Yeah, so see, like, it's this week's stuff, so I'm not going to go too much in depth with it because I can just go over it like next week or something. But I mean, laminar flow is just kind of like straight, smooth, easy flow. Turbulent, think like turbulence on an airplane, right? So the smoke will just kind of like be susceptible to more like random motion, essentially. But that's not as important. Like I said, it's more like concept, and this is more like for this week's stuff. But what's really important is flow rate. So flow rate is a measure of the volume of fluid passing through a given point in a given time. So specific volume divided by time. And so you have meters cubed per second as your SI units. And then the flow rate, that's equal to a specific area times the velocity. So we know that area is equal to meters squared, and then velocity is equal to meters per second. So then you can see meters squared times meters. That gives us meters cubed per second, which is the SI units for flow rate. So Q is equal to AV is our flow rate equation there, right? And flow rate, by the way, is also equal even if you have different densities of fluid, because density is not in the equation, doesn't apply. So as long as you have specific area, specific velocity, the flow rate will be constant, even if you switch up like densities and stuff. But here, if we have a radius of a garden hose, for example, that's a centimeter, and that hose can fill a 10-liter bucket in 20 seconds. Well, 10 liters in 20 seconds, that should be our flow rate, right? Because remember, our flow rate is the volume per unit time. So it's 10 liters per second per 20 seconds, right? That's 0.01 meter cubed in 20 seconds. So that gives us a flow rate of 5 times 10 to the negative fourth, right? If we want to figure out the speed of the water, then we know that Q is equal to the area times the velocity. And so you just take your area, the cross-sectional area of the hose, which is a circle, pi r squared, they gave us the radius there, and then you could just divide over and you get your speed, which is 1.6 meters per second. Now, with that flow rate equation comes the idea of the continuity equation as well. And it's the exact same thing. It's just a concept that tells us that, what do I want to say? The flow is constant at any point in the fluid, right? Even if you have a decrease in area or increase in area or whatever, right? Q is flow rate. Q is flow rate, which is the volume per second. So if you have a volume of an incompressible fluid entering a tube over a specific time interval, an equal volume must leave the tube, right? So the flow rate has to be constant, or the flow at least has to be constant, right? So whatever comes in, same thing goes out, right? Now, we can say this first point here with this larger area here, that's Q1. Q2 here, it's not like the fluid all of a sudden, like the amount of fluid going through per second is going to change, right? It's the same amount going in as going out. Now, how do we maintain that, right? If we have a decrease in area, there's like less room to move, basically, right? So if we maintain that the flow rate has to be the same, what goes in must go out, the same thing must go in, same thing must go out, right? Q1 is equal to Q2. Well, that gives us our continuity equation, which just tells us that everything is kind of continuous. That's why it's called continuity, right? Continue from A1 to A2, from Q1 to Q2. Everything has to be the same, right? Or at least like the flow rate has to be the same. Now, if we have a change in area, other aspects must change in order to maintain the same constant flow. So we know that Q is equal to AV. So A1 V1 is equal to A2 V2. The first area times the first velocity is equal to the second area times the second velocity. So we can see then, if we were to decrease area, right? If we had a larger area of 6, let's say meters squared, right? 6, and then we have a velocity of 2. That's 12, right? That's our flow rate, 12 meters cubed per second. Well, in order to maintain that same flow, what if I just decreased the area here? What if I made things a little bit smaller? Well, then my area all of a sudden goes down to 3, for example, 3 meters squared. In order to maintain that same flow rate with a decreased area, I have to speed up. So it goes 3 times 4, where 6 times 2 is equal to 12, 3 times 4 is equal to 12. So if I'm going slower in a larger area, I go faster in a smaller area. So if my area is larger, my velocity is smaller. If my area is smaller, my velocity is bigger, right? That's the idea here of the continuity equation. Now, once again, the volume flow rate has to be constant at all points, and so smaller area means larger speed or velocity. Larger area means smaller speed or velocity, right? So if you just think about, like, if you were to hold a garden hose, squeeze the nozzle a little bit, right? Same water has to be flowing in as flowing out, right? So if I squeeze it a little bit, you can see that the speed of the water there is going to increase in order to kind of maintain that amount of fluid going in and going out per second. The water has to speed up there to make sure that the same amount is flowing in as flowing out. But yeah. Now, if we're looking at blood flowing through a coronary artery partially blocked by deposits, which part of the artery is the flow largest? Well, based once again on the idea of the continuity equation, Q1 has to equal to Q2 is equal to Q3, right? Whatever. The flow throughout the entire portion has to be the same. You have to maintain the same flow of blood, right? the flow of blood is the same, but then if they're asking you about the speed of the blood, then we know that if we were to have a larger area, then the speed is less, or we move slower. Now, if we were to all of a sudden decrease that area, if there's a blockage in the coronary artery, then we should see a increase in speed to make sure that the same amount of blood is flowing through. So through the narrow portion, it's a smaller area, greater speed. Through the more relaxed portion, it's a larger area, smaller speed. Right? But there must be the same flow. So here we have the garden hose inside diameter of 16 millimeters. Hose can fill a 10-liter bucket in 20 seconds. So 10-liter bucket in 20 seconds, that's going to be our flow rate once again, right? Which is the 0.01 meter cubed divided by 20 seconds. And then we can kind of set that equal to our area times our velocity there. So our area is pi r squared. We know that the diameter is 16 millimeters, so our radius is 8 millimeters. That's going to be the same as 0.008 meters. So pi r squared, that gives us our area. And if we just divide over that area, we can get our speed, which is 2.5 meters per second, right? Now it says what diameter nozzle would cause the water to exit with a speed 4 times greater than the speed inside the hose. So the speed was 2.5, right, going in. Now, if I want to increase that speed, then what would I do to the hose? If I want to increase speed, what can I do to the hose to increase the speed of water? Decrease the area, right? So if I decrease the area, I increase the speed. So if I want to quadruple that speed from 2.5 to 10, right? 2.5 times 4 is 10. Then I'm looking for the radius that can do that for me. And so you end up with a radius of like 4 millimeters, right? Which is a diameter of 8 millimeters. But once again, you'd have to maintain the same flow, right? The speed might increase, but then you would have to have a much smaller area. Small area, greater speed. Large area, smaller speed. That brings us to Bernoulli's equation here, and how that relates to the continuity equation, right? So I should move over here now. I don't like this explanation as to how they kind of explain the pressure relationship here, but I'll kind of explain it in my way. This is how I learned it from the MCAT. So if you have this larger area, once again, based on the continuity equation, this larger area will have a smaller speed. This smaller area here, right here, will have a greater speed. So you move a lot faster, right? You move a lot faster in this smaller area. Now, they're telling you here that the pressure is higher at a point where the fluid is moving slower, and it's lower when the fluid is moving faster. So what they're telling you is that there's more pressure here than there is pressure here. Well, that might be counterintuitive, right? Because you would think that if you squeeze it over here, if you squeeze something, if you're putting like a lot of stress on something, you increase the pressure. If you're really pressing down on something, if you're squeezing something, you're putting pressure on it. So it would kind of intuitively make sense that you say that, oh, there's increase in pressure here. But this is where intuition kind of fails us. And that's why we have to think about things more in terms of equations, right? So with Bernoulli's equation, what he did was basically take your hydrostatic pressure equation and add another concept of pressure here. So initially, for hydrostatic pressure, we had pressure at A plus rho GH A. This is the left-hand side, for example, of the hydrostatic pressure equation. What he added to it was also half times density times the speed squared, right? Now, that's what you see here, right? And so when we're looking at his equation, there's actually, this is the way I like to explain it, there's two components here that we're looking at. This is what's called static pressure. And this is what is called dynamic pressure. Remember, this is like MCAT stuff here, but it helps to understand a lot better of what's going on. So the idea here is that you can think about this equation as kind of like a conservation effect or a conservation equation, right? Whatever I have here should be the same here, right? Static pressure, this PA plus rho GHA component, or this PB plus rho GHB component, static pressure is just the pressure, right, associated with a fluid that's static, right? Just based on the height of, or the depth of, right, of the liquid or the fluid, right? Static pressure, static, you're static, you're not moving. Just the pressure of the fluid due to its height without any motion. This is what's called dynamic pressure. There's, dynamic mean like movement, motion, changing, right? And so this is the pressure associated just with the movement of fluid, right? So if you think about these as two like big variables, like A plus B, right? And this is another A plus B here, or we can say like C plus D, for example, then we can see that, okay, well, if this term increases, right? If this term increases, then, and we're assuming, for example, let me say this. Let's assume that you're looking at 2 points at the same height, 0.2 and 0.3 at the same height, right? So just by looking at the heights, this term and this term should be the exact same in terms of heights. This term and this term should be the exact same, right? At least from looking from a height perspective. Rho GHB should be equal to rho GHA. It's the same density of the fluid because it's the same water, same gravity, and they're at the same heights, right? Now, just based on the continuity equation, we know that if you decrease that area, you increase the speed, right? So if VB, the area or the velocity through that smaller point, right? That more blocked path, for example, if it was like a coronary artery that was clogged, then there has to be increased speed here. So if I increase my speed, right? So if there's an increase in speed here, if this term ends up being like 10 and this term ends up being 5, right? What does that mean for my dynamic pressure? If I increase speed, what does that mean for my dynamic pressure? So would the dynamic pressure decrease if I increased my speed? Remember, dynamic pressure is this term here. If I increase the speed, what happens to my dynamic pressure? It increases, right? If I increase speed from 2 to 10, for example, then this whole dynamic pressure increases, right? Dynamic pressure would increase if I increase speed because it's the pressure associated with movement of fluid. If there's more movement, right, there's like larger speed. If the fluid is moving faster, then I should see an increase in dynamic pressure. Now, the concept here, once again, is like if you're looking at things from a perspective that there should be conservation, right? If dynamic pressure increases, if I want to maintain everything on the left-hand side equal to the right-hand side, something else has to change, right? So if I'm looking at this, right, and saying, well, I started off at pressure 0.2, and I ended up at pressure 0.3, they're at the same height, then these two terms cancel out because their HA would be equal to HB, or H2 would be equal to H3, and everything else stays the same, so these two would cancel, right? So if I have now PA plus half PVA squared is equal to PB plus half PVB squared, right? If VB is all of a sudden greater because of that smaller area means greater speed. If this is greater and my dynamic pressure is greater, if I'm moving, if there's more pressure associated with my motion, if this increases, right? Pressure at B has to go down to maintain the same left-hand side, right? So if I have 3 plus, well, I want to say 3. I want to figure out something a little bit easier here. Okay, or we can do that. So if I say pressure at A, pressure at 2 here is 6. And the dynamic pressure associated with my motion here is another 6, right? 6 and 6 is 12. That's what's, that's the left-hand side here, right? That factors in pressure due to the fluid itself based on its height and the pressure associated with the motion of the fluid there, right? That's equal to 12. Now, if all of a sudden I decrease the area and now my speed is greater, this might go up to 8, right? If I increase the speed here, my dynamic pressure might go up to 8 from 6, right? How do I maintain that 12 value? Well, then my pressure at B, right? Pressure at B here, or pressure at point 3, has to go down to 4. So 6 versus 4, right? So even though they're at the same height, because there's a difference in motion of the fluid, even though they're at the same height, because remember, normally you would say, oh, P2 equals P3 because they're at the same height. But since there's a difference in motion, right, the fluid is moving faster here at point 3 because of that smaller area, the dynamic pressure is going to increase because of that faster, right? Dynamic pressure will increase because of that faster moving fluid. And so it's like, if you just look at things like in terms of arrows, right? If I just look at static versus dynamic, if this increases, this section here has to go down, right? So there's these two sections here. So if this is less, if the dynamic pressure on the left-hand side, that more relaxed point, is less because you're moving slower, then the pressure, the static pressure associated has to be greater. So if you look at arrows, right, if I increase my dynamic pressure, I have to decrease my static pressure. If I decrease my, like if I moved backwards, for example, from this small area to this larger area, right? If I decrease then my speed and I decrease my dynamic pressure, I should see an increase in my static pressure. That increase in static pressure will not arise from a difference in height, because if we're looking at the same heights, it won't come from that, but it will come from the difference in pressure there. So the heights will be the same, just the absolute pressure will be different. And this is what's called the Venturi effect. This concept here that with movement of fluid, right, from one area to a different area, that difference in speed will cause a difference in pressure, even if they're at the same heights. And thus, if I experience a lower pressure here, right, if I experience a lower pressure here, like I said, if my dynamic pressure increases, then my absolute pressure has to decrease, or my static pressure has to decrease here, right? I go from 6 to 4 because I went from 6 to 8. And so if I experience less absolute pressure here, less static pressure due to the fluid, once again, pressure is equal to force over area, right? Less pressure means less force. So if there's less force here exerting on this column right here, right? If there's less force, then I should experience a smaller height, right? If there's greater force, greater pressure, I should experience a much larger height. And so that brings us to this quick check right here, right? Because it says gas flows from left to right through this pipe, whose interior is hidden. At which point does it have the smallest inner diameter? So if we're looking at inner diameters, right? Diameter, we think about area. If you have a smaller area, you have a faster speed, right? Smaller area, faster speed. So which one has the smallest area, or in other words, which one has the greatest speed? Well, the idea here is that if you have, once again, a bigger velocity or bigger speed, you have a smaller area. Bigger velocity, bigger speed means bigger or smaller area, my bad. And so if you have a smaller area, you have a smaller diameter, right? Now, once again, if you have that larger speed is going to cause a smaller pressure, right? A smaller pressure means less force. Less force, right, means that it's not going to be exerting a lot of force on this fluid to push it down a lot. So if there's a lot of force here, it's going to push down the fluid here a lot, right? It's going to push it down a lot more. So if there's more force, there's more pressure, right? There's greater pressure here, for example, at point C, because maybe at point C, the pressure is larger, because the fluid is moving slower. At PC, or PA, my bad, this pressure point at A here, right? It's a little bit in between. It's pressing down a little bit, right? It's in between, it's pressing down a little bit. But the idea here is that PB will be exerting the least force, or the smallest force right here. It's not going to be pressing down a lot. If it's not pressing down a lot of force, right, you don't have a lot of pressure. Therefore, it's pushing down the least with the least amount of pressure. So you can see that PB is the least pressure. And so if it's the least force, it's the least pressure. Smallest pressure will mean the largest speed. So it's moving the fastest at this point, point B. If it's moving the fastest, if you have the largest speed at that point, you must have the smallest area. If you have the smallest area, you have the smallest diameter. Does that make sense for this part right here? Okay. Yeah, it's not important. This lift stuff is not the greatest here. Now I just want to move on to this firefighter problem here is very important. I'm going to try to wrap things up here a little bit. Either that or, I want to see. So I don't know if I'm going to be able to, yeah, I don't think I'll be able to get through the whole quiz tonight. But I can certainly post the quiz that I have on Google Drive. I'll try to get through this. But this example here is telling us water is flowing in a fire hose with a velocity of 1 meter per second and a pressure of 2 atmospheres. So at the nozzle, where the water exits the hose, what must the pressure be assuming the water exits at constant velocity? Yeah, and I can post it with my work shown as well, so you guys can see everything. I believe I got 100 on this quiz, so I can post the answers. Otherwise, if I didn't, then I can just edit and give you the updated answers and stuff. But yeah, I can post the answer key and post my work, so you guys can see both, from a student perspective and from a professor perspective of what's going on. But what does constant velocity mean? Do you remember from the first couple of weeks? Exactly. And so if your velocity is the same everywhere else, right, or every single point, then your acceleration is equal to 0. You're not accelerating, right? And if you're not accelerating, then there's no net force. So if we're looking at pressure, remember pressure is force divided by area. Well, if there's constant velocity, there's no acceleration, there's no net force, then we should see no net force here, right? So we know that as the water exits the hose, when the water exits the hose here, right, what should be the pressure of water at that point? 1 atmosphere, right? Because it's going to be in contact with the atmosphere, right? So as the water's coming out of the hose, it's in contact with the atmosphere, so it should be 1 atmosphere, or 10 to the 5th pascals. Now, if there's no net force, right, based on the fact that it's constant velocity, if there's no net force, then we can think F net is equal to the force of the water coming from behind minus the force of the water from the front, basically, right? Or, my bad, other way around. I actually have it here, my bad. Yeah, F front minus F behind, right? And so there has to be a net force of 0 at that point. And there's 0 net force. That's because there's 0 acceleration, because there's constant velocity. And that means then the pressure from the front here should equal the pressure from behind, right? And so because the forces are the same, front is equal to the force behind, right? F front is equal to F behind, then pressure front is equal to pressure behind, right? And so the pressure behind the nozzle would also be atmospheric pressure. So it's also equal to 1, right? So in order for the F net to be 0, because of that constant velocity, pressure of the behind must be equal to 1 atmosphere as well, to exit at a constant velocity. Now for part 2, they said assume the hose is horizontal at a constant height. What is the velocity of the water exiting the hose? Well, this is just using Bernoulli's equation, because if you have PA plus rho GHA plus half PVA squared equal to PB plus rho GHB half PVG squared. If we're at the same height, then we can see that HA, HB should cancel out because they're at the same height, right? And so then you're just left with PA plus half PVA squared is equal to PB plus half PVV squared, right? So we know that water is flowing in with a pressure of 2 atmospheres. So A is in, B is out, right? And so we can see here then, we can kind of solve, we can solve for it, right? 2 atmospheres plus half PVA squared is equals 1 atmosphere plus half PVB squared. And then, what do I want to say? Yeah, they said flowing in with a velocity of 1 meter per second, right? So VA at least is 1, and your density is 1,000 kilograms per meter cubed. So half times 1,000 times 1 squared. We add this together. This is 10 to the 5th because I did 2 atmospheres minus 1 atmosphere. That's 1 atmosphere, and that's 10 to the 5th pascals. And then that's equal to half PVB squared. And then you can just solve for VB. This like flowing in pressure is different from like the pressure behind. When we're saying like pressure behind and pressure front, like we're talking about like immediately at the nozzle, like the pressure exactly here and exactly there. That's what we meant. But HA and HB are 0 because they said constant height. So assuming constant height, if the height at point A doesn't change from point B, then they will cancel out because the density is the same, gravity is the same. Does that make sense? But yeah, that's how you can get your velocity, right? And they said if the hose is not at a constant height, would the velocity of the water be bigger or smaller, right? So if it's not at constant height, right? What if they lifted it, for example? I don't know if they told us exactly how much they lifted it by, but if they were to lift it to another height, as they do in this picture here, where this height is different from this height, then you would actually have a rho GHB term here, for example. And so because there's a rho GHB term, right, our dynamic pressure, or my bad, our static pressure, like I said, static pressure is this combination here. Well, we went from having no term here, rho GHB isn't a term anymore, to now having it as a term, rho GHB, right? Because we now have a specific height. So then we can see that our static pressure goes up. So then our dynamic pressure has to go down to make sure that everything is equal. So in that case, in order for the dynamic pressure to go down, VB would have to be smaller, right? So that's the idea there. Or even let's say if they what is it? So the only reason I'm saying that they're canceling out is that these two terms would be the same. So even if you did have it, like even if you did keep them, right? PB plus rho GHB, if you were to just simply increase the height, that increases your static pressure. So your dynamic has to go down, right? So if I went from this static pressure of 3, or let's do that 6 one again. So if I went from a static pressure of 6, a dynamic of 6, to all of a sudden a static pressure of 8, right? Because I increased in height, then I have to have a dynamic pressure of 4. So my speed has to decrease to maintain 12 here and 12 there. That's the idea there. But that's the firefighter problem. This is just, once again, really simple. P1 and P2, these are just like some worked examples. They should be the same because they're at the same height. Here, if you're comparing all the different heights, P2 and P3 will be greater than P1 because they're at more depth. And then 2 and 3 are equal to each other because they're at the same height. This is continuity. Whatever goes in must go out. So if I have 10 plus 1 plus 2, right, that's 13 going in. I must have 8 plus 4, that's 12, and then 1 going out here as well. So what is the flow at the pipe marked with A, or this with a question mark, right? Then 1 milliliter would have to go out. 1 milliliter would have to go out, right, per second. So to maintain that constant flow. And then this is an example. I don't think it's like, I don't know if it's necessary to do this one, because this is like pretty much identical to the written homework problem that you guys have. And this is very similar to one of the quiz problems that I can go over. So I might as well just jump to the quiz, honestly. Because these are the exact same. But I can post these lecture slides as well to the Google Drive, so you guys have access to like these annotations and stuff. But let's move on to the quiz real quick and see if we can at least, we can probably, we can get through 1 and 2, I think. We can get through 1 and 2, but we might not be able to get through 3. But yeah. So for 1, fluid in a tube, the L-shaped tube has 1 open end on the left and 1 closed end on the right. Water fills the tube as shown in the figure and is topped off by 30 centimeters of oil at the open end of the tube. What is the gauge pressure at the oil-water interface? When they say oil-water interface, they just mean right here. What is the pressure? Oops, that's a huge pencil. What is the pressure here? Right, that's the pressure that they're asking for. And they're asking about gauge pressure, so remember you have to convert from absolute to gauge pressure at the end. So any ideas as to how we can kind of start this off? So I see hydrostatic pressure equation, and then now, I have a question. So should we start from this closed and then go upwards like this? Because remember, we're dealing with like different densities here, right? Because remember what I said about the interface, you're dealing with like oil and water here. And so don't you think it would be a little bit easier to just measure from here to here? Because you have here, this is your P bottom essentially that you're looking for. And here's at the top, this is your atmospheric, right? Because we really don't know what the pressure here at the close is going to be. Because from closed to here, well, we don't know what the closed is here. If we wanted to figure out the closed, then we have to compare the atmospheric here. And the issue with that is that you're combining 2 different fluids. You're going from oil to water. So it's like you would have to combine pressure of oil and water to get to the closed, and then from closed back up here. Do you see where I went there? Does that make sense, Eric, as to why we couldn't do that? Yeah. So you definitely just try to keep it where you're analyzing the same liquid at a time. Because otherwise, like if you start from the closed, right, and you go to the top here, well, the top is what or at least like the interface is what we're looking for. The only way we can figure out the closed is if we compare it to the very top here, the atmospheric, and that's going to be a combination of oil and water, and that's going to be a pain to calculate. I don't even know if you could calculate that. Exactly. But yeah, so we can just compare it to here and here, right? So we have PA plus rho GHA is equal to PB plus rho GHB, right? And so we have the bottom height, we can just call that a reference height, and that's just 0, so this whole term goes to 0. And then our pressure at the top, here, PA, well, that's in contact with the atmosphere. So that should be what? 10 to the 5th pascals, right? Alternatively, I mean, yeah, I personally think it's better to calculate for absolute pressure first and then calculate for gauge pressure later, because they might ask you for a part later on, and that might need absolute pressure. So you can always get the absolute pressure easy. Gauge pressure is even easier to just convert to at the end. So I would personally put 10 to the 5th pascals, and then multiply by add density of water times the gravity, or not density of water, my bad, density of the oil, which is 700 kilograms per meter cubed, times 10 meters per second squared, times the height, which is 0.30 meters, right, is equal to PB. Now, once I get that, whatever answer that is, I can just subtract what to get my gauge pressure? Because remember, this is my absolute pressure. So how can I get to that gauge pressure? Exactly, it's 1 atmosphere, or make sure that if it's the same units, right? So if we're working with pascals, you subtract 10 to the 5th pascals. So if I subtract 10 to the 5th pascals from this whole thing, then it would just simply be, the answer would just simply be 700 times 10 times 0.3, which is 2100 pascals, right? So you just take this whole thing, subtract minus 1 atmosphere, right, to get your gauge pressure, which is the same as 10 to the 5th pascals, which is 760 torr, which is 760 millimeters of mercury, right? Just make sure you have the same units that you're working with throughout. But you take this whole thing, minus 10 to the 5th pascals to get the value in pascals, which is 2100 pascals. Now the gauge pressure at the top of the closed tube, right? So we want to figure out the top of the closed tube. Well, we can go, actually, no, never mind. I will let you guys do this one again. So what do you guys think? How can we get this closed tube pressure? Same equation, right? So if we have rho A, or not rho A, PA plus rho GHA is PB plus rho GHB, right? Well, A, let's call this A at the top here, B at the bottom. B, once again, is our reference height, so this goes to 0, right? We're trying to figure out B at the bottom, PB here versus PA. Well, we already have what PA is, right? That is the, what we can do is, this equation, you can either use absolute pressure or a gauge pressure. And so I just have the gauge pressure handy. If I use gauge pressure here, my answer is going to be in gauge pressure there. If I use absolute pressure here, my answer is going to be in absolute pressure there. So if I wanted to use gauge pressure for PA, which is the 2100 pascals that I had access to before, right? 2100 pascals, right? We said PB was 2100 pascals, but we referred to this as PB and this is PA in the first problem. Now we're referring to this is PB and this is PA. Once again, you start from the bottom, go to the top, right? So I just call B as in bottom, A as in top, right? A at the top, B at the bottom, right? So A now is at that oil interface, B is at the closed portion, right? So HB is 0 because we're working from the bottom upwards. So then we're just left with PB is equal to PA plus rho GHA. And so now you're working just with water. So our density is going to be 1,000 kilograms per meter cubed times 10 meters per second squared, right? Times, well, that doesn't work out. Times the height at A. And the height there, that's from here to here, right? Or from here to here. That should be what? If this from here to here is 100, right? This is 40. Then this part is 60. If this is 30, then this is 30. Right? So that's what, 30 centimeters, right? So that's 0.3 meters. And so if you just add those two together, right? What should you get? Let me calculate this out real quick. Yeah, 5100. Yep. So PB is equal to 5100. I actually think they made a mistake on the answer key here. They have it as PA minus rho GHA. It should be PA plus rho GHA. But yeah, this is 100% right here. So we have 200 pascals. And like I said, this is going to be our gauge pressure. If they were to ask you about absolute pressure, what would you do? How would you convert this to absolute pressure? You add at one atmosphere, right? Or you add 10 to the 5th pascals. So just this plus 10 to the 5th pascals gives you your absolute pressure there, right? So P gauge is equal to absolute minus atmospheric, right? If I want my absolute, then I just take my gauge plus my atmospheric. But yeah. Now how about for number 2? If fluid flows through a pipe as shown at the right, the radius in the narrow region is RB here is equal to 1/3 RA. So it's here is 1/3 of the radius as compared to A. What is the ratio between the speeds at the 2 points? VB divided by VA. What do you think we can use for this problem here? Flow rate equation, right? And specifically a continuity equation, right? Because we're comparing 2 different points. Excellent. So Q1 we know has to equal Q2, and the flow has to be constant. And then A1 V1 is equal to A2 V2, right? Well, A1 is going to be equal to pi R1 squared, or let's say pi RA squared. Pi RA squared, right? And then, oops, my bad, not equal, not yet. This is our area, right? And this is VA. And then this is equal to pi R, what is it? So RA, yeah, so this is RA is equal to RB, okay, my bad. RB is equal to 1/3 RA, right? So to avoid the 1/3 stuff, because I don't like fractions, you can just say that RA is equal to 3RB. So RA is equal to 3RB, right? And so actually what I can do is then just, okay, so it's going to be weird. But if RA is equal to 3RB, then I can just say this is 3RB for my, that's so bad. I don't know. Okay, let me just, because I don't want to erase because there's the answer underneath it. But if we're just writing this out, PRA squared, because if we're just taking the area of A, it's pi RA squared, and RA is equal to 3RB based on this relationship here. So if RA is equal to 3RB, then pi 3RB squared, that's our area there, times VA. And then we have pi RB squared times VB, right? Now we can kind of compare the 2 equations here. Pi is pi, that cancels out. We have 9RB squared VA and RB squared VB here, right? So this cancels out with this. Then you're left with 9 VA is equal to VB, right? If we divide over VA, we can see that VB over VA is equal to 9, right? So that's that ratio there. It's 8:04. I don't know if I have enough time to go over this stuff. I mean, A is pretty simple. It's just asking you about the gauge pressure at the left end and the absolute pressure. So they're saying if this is our gauge pressure, 225 kilopascals, what is the absolute pressure? 3 is the last question, yeah. It's just a longer question because it factors in Bernoulli and all of that. But you know what? Okay, might as well. It's it's the same as homework, but now that I'm looking at it, it doesn't seem too bad. So let me just do it. If this is the gauge pressure at the left end, 225 kilopascals, P gauge is equal to 225 kilopascals, right? They're asking us about the absolute. We know that P gauge is equal to P absolute minus P atmospheric, right? If I want to figure out my absolute, what do I need to do? Add 10 to the fifth, right? So absolute would be equal to P gauge plus atmospheric. So if P gauge is 225 kilopascals, I would have to add the atmospheric pressure. So 225 kilopascals. Atmospheric pressure is also 100 kilopascals. You can say that. And you can leave your answers in kilopascals if you want to. So you get 325 kilopascals as your absolute pressure, right? Which is the same thing as 325,000 pascals. So if you wanted to, you can convert from kilopascals to pascals, and then just leave your answer in pascals. Doesn't really matter. They don't have a preference or a requirement here at all. But yeah, it's 325 kilopascals or 325,000 pascals. Now, if they're asking about the absolute pressure at the right end, well, there is a change in speed, right? And also a change in height. So which equation do you think we can use here? So we're trying to compare two pressures. The long one that starts with a B, Bernoulli. The long boy equation. I remember there's this equation that my calc teacher in high school would talk about. It was Calc 2. It was like some odd, long Taylor series or something. I think it was like n to the n or something like that. But he would refer to it as the Big King Mac Daddy function. So I will refer to this Bernoulli equation as the Big King McDaddy function. Bernoulli equation is the Big King McDaddy function. So it's the very long equation with all the terms. PA plus rho GHA plus half rho VA squared. PB plus rho GHB plus half PVB squared. This is the big King McDaddy function. So, yeah. So we have our pressure here. Remember, we got our absolute pressure here earlier, so we can plug that into PA. You can say this is PA. Well, it's kind of weird because I don't want to. Okay. We can call this PB actually, because like I said, P is like bottom, A is like the top. So I prefer that a little bit better. So we can call PB as our bottom equation, right? Or bottom pressure. So we can say that PB is 325,000 pascals, right? And then we have density of what? Is it oil? Yeah, 600 kilograms per meter cubed. So 600 times 10 times the height at the bottom here. Well, actually, yeah, HV should be 0. My bad. So it actually doesn't even matter for that part. Let me just erase that. My bad. Thank you for catching that. So height at the bottom is just 0, so it doesn't really matter. Now we're just adding half times 600, which is the density, times VB squared, and the VB was 3 meters per second. So 3 squared, right? And then we're setting that equal to the pressure at A that we're looking at, that we want to figure out, plus 600 times 10 times 10 meters, right? That was a height. And then plus 1/2 600 times, what is it? 4 squared. Sorry for the tight there, for the tight equation there. But once you calculate that out and solve for PA, what you should get is 262,000 pascals, I believe, or 262 kilopascals, right? Now, if they're asking you about the gauge pressure, right? How can I go from this absolute pressure to gauge pressure? Exactly, subtract 10 to the 5th pascals, right? Or 100 kilopascals. So I go from 262 kilopascals minus 100 kilopascals. That gives me 162 kilopascals as my right pressure gauge reading. So, not too bad. Been just 10 minutes late, sorry about that. But I just want to make sure that you guys understood this stuff here. This problem in the lecture slides is, you already saw, like it's pretty much the exact same idea. same thing here. Like you can see like this same pressure gauge stuff as well. So it's not too bad. But I can send you guys or upload this on the Google Drive as well, so you guys have access to this. And then, well, I already have this worked out, but I can still upload the quiz. You guys have access to that as well as my like worked out solutions from the quiz that I took. So I think with that being said, I'll probably end the session on that note. Apologize for the very long session tonight. But yeah, and I can also post the lecture slides. Yeah, but that's been it. Hope you guys really enjoyed this one. I wouldn't say, I don't know if you guys enjoyed it, but at least you guys found it helpful, hopefully. So, yeah, I'm not sure if I'm going to be on campus tomorrow. I'm just like, I know I haven't been there for the past couple of weeks, but I've just been like swamped with work. So, yeah, I might not come tomorrow, but we'll see. I don't know. But, I mean, for those of you who've been asking questions and sending me DMs, you know that I reply as soon as I can. And if I'm not able to, at least like I'll apologize. So I'm at least good about that. But yeah, that's it. So hopefully you guys found this helpful, and yeah, hope you guys enjoy the rest of your night.